Imagine a highly fortified, modern industrial facility. Now introduce an extreme, intentional kinetic impact directly to its structural core. The immediate result is a catastrophic cascading failure. The shockwave severs primary defense grids, racing outward until the network is plunged into darkness. Historically, nuclear safety regulations focused on mitigating design basis accidents. These are predictable, naturally occurring events like severe earthquakes or localized tsunamis. The 2011 Fukushima disaster redefined the baseline for safety. Regulations expanded to mandate severe accident mitigation, designed to counter a total loss of on-site power. But standard severe accident mitigation relies heavily on the principle of redundancy, having a primary system plus a secondary backup plus a tertiary backup. That mathematical model assumes failure modes are accidental. It assumes the backups will not be intelligently targeted. An intentional extreme attack introduces an entirely new variable. A targeted strike is designed to bypass and neutralize all redundant systems simultaneously. To counter this precise threat vector, Japanese regulators introduced a strict mandate, the creation of a Tokuju facility, or the specific severe accident handling facility. Engineering a Tokuju requires an entirely independent, physically isolated architecture. We are going to engineer the parameters of a Tokuju facility from first principles, establishing the 4 structural and operational pillars required to meet modern regulatory standards. To survive a targeted attack, structural engineers must abandon the standard logic of redundancy in favor of zero-trust autonomy. This architectural schematic of a post-Fukushima reactor shows primary cooling loops and severe accident backups closely clustered together. If an intentional massive impact occurs, a localized blast radius neutralizes the primary site and its backups. The entire cluster goes offline. Engineers define this as a common cause failure. Redundant systems provide no protection if a single kinetic event destroys them all at once. This forces our first pillar, physical isolation. We extend a measuring line outside the potential blast radius to establish a safe zone for the Tokuju Foundation. Within this isolation, engineers implement technological diversity via segregated piping routes, bypassing compromised zones. The Tokuju facility itself remains a potential target, requiring our second pillar, structural robustness. It must be built to withstand a direct, heavy aircraft collision. To achieve that level of kinetic resistance, the architecture relies on subterranean placement, thick concrete shielding, and severe accident-grade internal equipment. By combining strict spatial isolation with extreme kinetic robustness, engineers eliminate the physical possibility of a single attack vector disabling the entire site. Let's look at the secondary failure state. The initial physical impact has completely severed the site from the national power grid, and external water intakes are destroyed. A true Tokujuku classification requires the third pillar, infrastructural autonomy. The facility must operate entirely solo for a sustained duration. Inside the isolated Tokujuku footprint, new nodes light up, representing internal power generation and self-contained water reserves, pushing active cooling lines straight toward the dead reactor. That leaves one final operational vulnerability. What happens if the main central control room is violently occupied or completely destroyed, dictating the fourth pillar, security and alternative control? The mandate requires a hardened alternative control room. This underground bunker utilizes encrypted telemetry lines, completely bypassing the compromised main room. From this remote desk, operators must maintain the ability to force a reactor shutdown, initiate continuous core cooling, and depressurize the containment vessel. These pillars establish the Tokuju as an autonomous command tower, a dedicated system capable of fighting a catastrophic event entirely on its own. This matrix outlines the formal legal classification. You can see a strict 3-tiered hierarchy. While the bottom tiers prevent normal accidents and mitigate internal failures, the top tier, Tokuju, serves exclusively as the final backstop against targeted, external total loss events. The ultimate litmus test for this classification is a single question. If all existing safety measures are neutralized, can this facility alone prevent catastrophic reactor failure? Meeting that mechanical standard creates an immense logistical hurdle for the energy sector and structural engineering firms tasked with implementation. The Nuclear Regulation Authority mandates strict installation deadlines. If construction is delayed, the regulator holds the legal power to force immediate plant shutdowns. The capital required is massive. A single Tokuju facility costs hundreds of billions of yen, requiring years of highly complex civil engineering to complete. These financial stakes dictate the daily realities of engineers working in corporate headquarters, managing exact regulatory technicalities in administrative centers far from the reactors themselves. Tokuju represents zero-trust engineering in its most literal form, an autonomous, hardened fortress designed so that even under intentional destruction, catastrophic failure is mechanically impossible.